Hello and welcome to lecture 44 of analog integrated circuit design. So far we have looked at a number of circuits starting from simple amplifiers to fully differential op amps. Now we have used some simple models and hand calculations to characterize these to get an idea of what they do. Now this is essential for understanding the basics of these circuits and then to design them, but finally to characterize these circuits completely you have to resort to a circuit simulator, because the behavior of each device is very complicated, and when you connect a number of devices together and if you put in all aspects of each device, it is impossible to calculate anything by hand. So, there are many simulators that are available, which I will call SPICE like simulators. SPICE was one of the early simulators that enabled analysis of complicated circuits, and there are a number of simulators available today which operate on that principle. So, in this lecture what we will do is to look at the kind of analysis that are possible in a simulator and how to use them to characterize the circuits we have discussed so far. This is not meant to be a manual on simulators. For that there are detailed manuals for each simulator which you can consult for the syntax and the way to use the simulators and so on. This is more to get an idea of the principles behind the simulator, not in great detail, but just enough to use them. Okay. Now, what do we do when we encounter a circuit? So, let us say the circuit is of this type. I will show some simple circuit for illustration, but this applies to any circuit that we want to analyze. This has RC and a diode and some voltage source. So, what we do always is first compute the DC operating point. Now, based on the DC operating point, we may do a small signal incremental analysis with an increment applied to various points of the circuit. And finally, we may also be interested in doing a large signal analysis with time varying inputs. Okay. Now, while doing hand calculations, we normally do this in a simple way, that is, we simplify the models and do this one, and we also do the second one, small signal incremental analysis, again somewhat simplified. And this last thing is usually something that cannot be done by hand analysis except for very trivial circuits. Okay. And for this, usually for any circuit for which you need to do this, you need a simulator. Okay. So, the basic analysis that are provided by the simulator are these three. Okay. So, there is an analysis called DCOP. This gives you the operating point, and there is an analysis called AC, which is for small signal incremental analysis, and finally there is an analysis called TRAN or transient, which is for large signal and time varying signals. Okay. Now, the simulator is basically a software to which you have to provide some inputs, and it will do various analysis on the circuit and give you the outputs. So, what are the things that you need to give to the simulator? First of all, you have to specify in some way what the circuit is. So, let us again take this simple circuit, and you have to specify the interconnection of various components and specify the components, and this is usually done by drawing the schematic with on the software or by specifying the netlist. You can consult the simulator's manual to see how to do this. Now, what the simulator will do is to set up modified nodal analysis equations which are nonlinear in general, because we have nonlinear elements, and solve the equations. Okay. Now, as you know, for nodal analysis, the variables are voltages at different nodes with respect to a reference node. So, the circuit also needs to have a ground or a reference node. Okay. That is what is the bottom node in this circuit. And finally, let us say in this very simple circuit where there is only one variable to be solved for, V1, I will quickly write down the expressions. The current through the diode plus the current through the capacitor plus the current through the resistor has to equate to 0 by Kirchhoff's current law, and these currents are a function of V1. Okay. So, what do we have? The current through the capacitor is C dV1 by dt plus the current through the diode is some nonlinear function of the voltage V1 plus the current through the resistor is V1 minus Vs by R, which is usually written as V1 by R, and the constants are on the right hand side. Okay. This is the equation for a very simple circuit. For a more complicated circuit with so many nodes, you will have a number of different equations, and each of it could be nonlinear. Okay. So, in addition to specifying all these, you also need to specify device models. Okay. Device model simply says, for instance, for a diode what F is and so on. Okay. So, there are device models available publicly and usually also in many reference books, and you can use these things in order to run simulations on some basic circuits. Okay. First, let us look at the DC operating point. By definition, it is for DC. So, what the simulator does is to open circuit all the capacitors and short circuit the inductors and basically do nonlinear analysis. Okay. For our particular circuit, the capacitor would be omitted and we would have only the resistance and the diode. Okay. So, let us say this voltage were to be 5 volts, then the simulator will calculate the currents flowing in the circuit and also the voltage at every node in the circuit, and from this you can get all the information about the circuit. Okay. Now, what do we do normally when doing hand calculation for a circuit like this? We assume that the diode has 0.7 volts across it in forward bias. Okay. The reason we do this is we can't solve nonlinear equations easily by hand. So, we assume that, but if you use a simulator, you will get exactly what the voltage is depending on the diode. Okay. Depending on the saturation current of the diode, there will be a particular voltage across it, and that is what you can find exactly from the simulator. Okay. And the next analysis that the simulator provides for, which is very frequently used, is known as AC analysis, and this is basically an analysis of the small signal incremental equivalent circuit for sinusoidal steady state. okay, where the increments are not arbitrary, but the increments are sinusoids at whatever frequency you wish to analyze at. And also it calculates the steady state. Okay. So, this basically gives you the sinusoidal steady state for the incremental equivalent circuit. Okay. So, what does it mean? Again, let us take our very simple circuit. This is what we had, and perhaps now I will have an incremental source in series with this 5 volts. Okay. Let me assume that that is the case, and I have some V p sin omega t, and the size of V p, the magnitude of V p is such that small signal analysis is valid. In such a case, I can use this AC analysis. So, if I draw the incremental equivalent circuit from these two, I will have an increment of V p sin omega t, the resistor remains as it is, the capacitor remains as it is, and the diode will be replaced by its linear small signal equivalent R d. Okay. So, now this is by definition a linear circuit. Okay. So, that means that the magnitude of V p does not matter, whatever V p you choose, the signals in the circuit will be proportional to V p. Okay. Now, this is an important point, because one of the other kinds of analysis that we do is to apply sinusoids to the circuit and find out distortion, because we have nonlinear elements. If you apply a sinusoid at a certain frequency, at the output you will also see sinusoids at the harmonics, or if you have sinusoids at multiple frequencies, you could see intermodulation components. But this analysis cannot be used for that. This by definition does only the analysis of the linear incremental equivalent or linear small signal equivalent circuit, and that which is by definition linear. So, if you put in a sinusoid at a certain frequency, you will only get sinusoids at the same frequency. Okay. Now, normally one of the things that we wish to determine is the transfer function of a circuit from a certain source to certain nodes, and for that a convenient value of V p to choose is 1 volts angle 0 degrees. Okay. So, in that case the voltage that you measure here will give you the transfer function magnitude and phase of the will give you the magnitude and phase of the transfer function. Okay. So, that is a very convenient value to use, and because this is analyzing a linear circuit, the size of V p does not matter. Okay. It is already assumed that V p would be small and you have got the linear equivalent circuit. So, whether you apply V p of 1 volt or 1000 volts, the output will simply change in proportion. Okay. Now, because this is such a frequently used analysis, the simulator also provides you certain other convenient features. Normally, you do not have to specify 2 voltage sources like this. Wherever you have either a voltage source or a current source, you can specify the DC value and the incremental values for AC analysis in terms of the magnitude and phase. So, let us say I would want V p to be 1 volt, okay, and I want 1 volt sin omega t. So, then the AC magnitude would be specified as 1 and the AC phase as 0, okay, and in most simulators the sin omega t corresponds to 0 phase. So, this is basically equivalent to having a 5 volt DC source and 1 volt angle 0 degree sinusoidal source for sinusoidal steady state analysis of the small signal incremental circuit. Similarly, you can do the same for a current source. You can specify a DC value of 1 milliamp and let us say AC magnitude of 1 microamp and AC phase of 0 degrees. This is equivalent to having a current source of 1 milliamp in parallel with another current source which has 1 microamp angle 0 degrees of sinusoidal value. Okay. It is a sinusoidal source of 1 microampere angle 0 degrees. Okay. Also, what this AC analysis allows you to do is to sweep the value of omega, because here we have not specified the value of omega. Once you have the incremental equivalent circuit like this, you can calculate it as a function of omega. This is what usually you are interested in plotting Bode plots and the magnitude and phase response. Okay. So, you can sweep omega in different ways, linear, log and so on, in a number of ways, and plot the results. Okay. So, what you get out of this analysis is the magnitude of the voltage. So, let us say across the capacitor you have V1, you can plot the magnitude of V1 and the phase of V1. Okay. So, it could look like that, and then the phase could look like that. Okay. A very useful analysis. You have already seen how often we do small signal incremental analysis of our circuits, and that is done using AC analysis on the simulator. Okay. And finally, we have transient analysis, which, as I said earlier, is the real reason to use simulator, because this is almost impossible to do by hand for anything but the most trivial circuits. So, let us say again I have a particular case I am looking at here. I have this 5 volt and I could have some increment, but this is not necessarily a small signal increment, this could be anything. Okay. I am just showing it like that, the increment could be anywhere else in the circuit. And by the way, this increment also could be, let us say, a sinusoid of some frequency, or it could be something else. It could be a pulse of some shape, and also these days simulators will allow you to specify arbitrary waveforms using some piecewise linear definition. Okay. You could specify anything you want, exponential, sinusoids, pulses and so on, all the commonly used shapes will be there, and you can even specify arbitrary shapes. So, what the transient analysis will do is solve the nonlinear differential equations with time varying inputs. Okay. And in this case, because you are solving the nonlinear differential equations, for instance, if you put a sinusoid, the amplitude of the sinusoid will make a difference. Okay. And why do we use this transient analysis? With a sinusoidal input, normally you would try to calculate the distortion produced by the circuit. Okay. That is, you put in a sinusoid at a certain frequency and you do the analysis, and you can, by taking the Fourier transform of the output, whatever the relevant output is, you can determine the strength of the harmonics. Okay. And as you know, if you have an amplifier, for instance, the harmonic distortion is a very important criterion, and that is computed by doing a transient analysis. Okay. And another thing of interest usually is step response, and this is computed by using a pulse of appropriate size. Okay. And you could do this for small or large signal, and for linear or nonlinear circuits. In case of linear circuits, step response characterizes the transfer function, and in case of nonlinear circuits also you may be interested in how the circuit behaves when you apply a step. Okay. And of course, you could apply any other kind of signal and also evaluate the response. Like for instance, one of the interesting things is, let us say you have a circuit that is powered by some power supply. This again is a commonly used analysis. One of the interesting things is how the circuit starts up. Okay. When you power up the circuit, does everything come up correctly or not? So, for that what is normally done is, the supply voltage is stepped up or ramped up at a certain rate from 0 to its value, whatever it is, let us say 3.3 volts, and then you examine what happens in the circuit to see that everything comes up. Okay. Now, this is again a non-trivial thing, because of non-linearity and complicated feedback loops. Sometimes there could be a situation where if you analyze the circuit with a 3.3 volt supply, everything looks fine, but if you start it up from 0 and go all the way to 3.3, it does not reach the right state. Okay. There could be some complicated feedback loops which latch up to some other value and so on. So, this is again something that is very important. This mimics reality, right. So, you have a circuit, you put a battery on it and then you turn on the circuit, you would like to see whether it starts up in the correct state or not. Okay. And how are all these things related? So, let us say we have the DC operating point that we analyzed for this circuit. Let us say for 5 volts. Okay. Let us say you make a small change to one of the sources, let us say 5.001 volts. Okay. Now, the result, the difference that you get between when you apply 5.001 volts and 5 volts is the increment, and that will correspond to what you get from the AC analysis for an increment of 0.001 volts at omega equal to 0. Here we are talking about omega equal to 0. Okay. So, if you do the DC operating point analysis for let us say a small slightly changed voltage source or current source, the same result can be got from AC analysis at 0 frequency, and this will be valid as long as the increment in the DC values are rather small. Okay. Similarly, let us say you have a transient analysis setup. And let us say Vp is small. What does it mean for it to be small? It means that the small signal assumptions are valid. In such a case, let us say you determine the voltage across V1 and it will also have a sinusoidal component, which will have a different amplitude from Vp, and it will also have a phase shift compared to the input sinusoid. Now, what you get from this analysis would be the same as what you get out of AC analysis for an increment of Vp at omega. Okay. You apply Vp angle 0 degrees at a frequency of omega. In case of AC analysis, you would have replaced this, not you, the simulator would have replaced this by its small signal incremental resistance. Okay. And you do AC analysis on this circuit. Let me put down the original circuit. and find the magnitude and phase of this, you will get some amplitude and some phase, and here what you would have got would be V 1, let me call this V 1 p, V 1 p sin omega t plus phi. Okay. So, a transient analysis with a sinusoidal input and a very small amplitude will give you the same result as AC analysis. Okay. Now, the AC analysis is by definition linear. So, that will correspond to what happens with a very small input signal. Now, these are all things that you can try out, especially when you are beginning to use a simulator, just so that you get used to what different analyses do and also how to do the analysis themselves. Okay. Now, in addition to these, the simulator provides many convenient facilities such as sweeping either the DC value or some component parameter, or you can have design variables in the circuit. Okay. You can consult the simulator's manual to see how to do these things, but the point is you can run the simulator only once, and let us say you want to calculate the DC operating point of the same circuit that we had all along. Let us say for different values 3 volts, 4 volts and 5 volts. You do not have to set up the circuit 3 times and then run the simulator 3 times. You can specify that this voltage takes on 3 values. The simulator will go and analyze it 3 times with the 3 different values and give you the results. Okay. And these are all convenient features. This is just so that you have to do less work and you can get the results more conveniently. Similarly, you can also change the component parameters and see how the circuit behaves. Sometimes you may want to vary some component value in order to optimize it, or in order to just study the behavior of the circuit. So, that also is possible. Okay. And in addition to these things, there is a number of other more sophisticated analysis such as periodic steady state and a number of others which are suitable for specific circuits. There are a number of circuits that operate with periodic inputs and attain a periodic steady state. For that, the periodic steady state analysis is useful. So, again these do not fall under the basic analysis and we will not read them here, but you can look at the simulator's manual and the extensive information that comes with it to find out about these things. Okay. And besides analysis, what you can also do in most cases is convenient post processing. Okay. This could include, for instance, for computation of distortion, you have the Fourier transform, the discrete Fourier transform that is available, and you can plot the results in a number of ways, number of convenient ways for visualization, and then for instance you can compute the rise fall times of step response and so on. Okay. So, these are all convenient additional features to the simulator. Now, the simulators have evolved over last 40 years or so, or maybe even more, and by now they are extremely sophisticated. Okay. So, you can analyze very complicated circuit with thousands of transistors or even more using these simulators. For instance, the tablet PC on which I am giving these lectures has a number of integrated circuits which were also simulated using these simulators. Okay. But you should first get familiar with the basics of the simulator. For that, you can try the DC operating point, AC and transient analysis on simple circuits, and make sure that they conform to what you calculate by hand. Okay. So, after that you will get some confidence in using the simulator and you can go on to analyze more complicated circuits. So, that is about the basics of the simulator. And one other type of analysis that is very commonly used and very convenient is noise analysis. Okay. You have a circuit with a number of components, let us say capacitors, resistors and MOS transistors and so on. What noise analysis does is to add appropriate noise sources to each component. For instance, this could be current sources in parallel with resistors and MOS transistors, and you have to specify an input port or a voltage source and a pair of output nodes. Okay. And you need this because this analysis will calculate the output noise at the specified output. Okay. And also the input referred noise referred to the specified input. So, you may have a number of inputs and outputs in the circuit. For each output you have to do the analysis separately. You should specify the output at which you want to compute the noise. You should also specify the input source referred to which you want to calculate the input referred noise. If you recall, the input referred noise is an equivalent noise that if you apply the input of a noiseless equivalent circuit, you will get the same output noise. Okay. And also one other feature of MOS simulators is that you cannot specify a current as the output quantity. What you can do is use an ideal current controlled voltage source and specify that voltage as the output quantity, and that will give you the noise in the current. Okay. So, again by practicing with a few circuits you will be able to get a hang of this one. So, just as a quick recap, here I have shown an example circuit. So, we want to do operating point analysis, small signal AC analysis with large time varying signals. So, what I suggest you do is take it as an exercise, and first of all you can do a hand analysis for this, assuming 0.7 volts drop across the diode, and then you do a operating point analysis, DC OP analysis, and find the diode voltage and current and see how they differ. Okay. Because the voltage across the diode will not be exactly 0.7, it will be somewhat different. So, again you can do the AC analysis. Let us say first you do it by hand, you calculate what you get out of the linear small signal equivalent circuit, where you replace the diode by its small signal equivalent circuit, and find out what comes out, the incremental VD that comes out. And then you do the simulation, you do the DC operating point and the AC analysis and compare the results. You can also do AC analysis over a range of frequencies, and you can also try and see what happens if the amplitude that you specify for the AC analysis is changed. Okay. As I mentioned earlier, this is for a linear circuit that it does the AC analysis. So, the outputs should simply be proportional to the input. Now, of course, you can also compare the results to hand calculations. And like I said before, the amplitude here does not matter. So, it is very common to use 1 volt of AC, and what you get out is the transfer function of the circuit from this source to this output. Again, next thing is to try and do transient analysis with a simulator. So, you first apply a small sinusoidal source in addition to the DC value and do the transient analysis, and you go on increasing the amplitude Vp and see what happens to the output waveform. In this case, the result will be different from that of AC analysis, and that is interesting in itself. And what you can also do is to compare the results when the signals are very small to what you calculated by hand and also what you calculated using AC analysis. Like I mentioned earlier, you can do a DC sweep for instance, you sweep the values of these voltages and plot the diode voltage across the input voltage. You can also plot the diode current across Vd and get the characteristics of the diode. Similarly, here you can do a transient analysis or an AC analysis by sweeping the value of DC. So, for different values of DC you can do the transient or AC analysis. Okay. And you can take a linear circuit like this and calculate the transfer function, that is, you plot the magnitude of V naught by Vi and the angle of V naught by Vi, which together give you the sinusoidal steady state response, or basically give you the transfer function of the circuit for sinusoidal inputs. This is something that is very commonly required. You can do the noise analysis for a simple circuit like this. We already know by hand calculation what the result must be for this particular circuit, and we know what the integrated noise across the capacitor is. You can also verify this using simulation. Similarly, for a MOS transistor circuit, you bias it at a certain value, let us say VGS of 0.7 and VDS of 0.7 volts, and measure the spectral density of the current noise of the MOSFET, and you can also plot it and find out the flicker noise corner where the thermal noise becomes equal to flicker noise and so on. You can also change the size of the transistor and see how the noise behaves. Okay. And you can plot the transistor characteristics, okay, to get approximate values of let us say mu and Cox and the threshold voltage and so on. So, you can plot ID versus VDS for different values of VGS. You can also plot ID versus VGS. You have to choose which one to sweep, either VGS or VDS, and you try it for different W by L and so on. So, again this will first of all help you get used to the simulator, and also for the transistors you have, it will let you estimate the characteristics. And in addition to VGS and VDS, you know that the bulk source voltage also has an effect. So, for a fixed VGS you can sweep VBS and see, okay, because earlier I said that the bulk acts as another gate to the MOS transistor. You can verify using this exercise whether it is indeed the case. Okay. Now, please go through all the exercises I just mentioned. As I said, it will first of all let you get used to the simulator, because it takes some time to get used to it and get the simulator to behave the way you want, and it will also help you confirm what you already know about circuits using simulations. Now that we have the simulator, one of the important things that we need to calculate besides transfer function and so on is loop gain of feedback circuits. Okay. Let me take a simple example of an op amp amplifier. I will take the prototype non-inverting amplifier. I will also show the power supply in this case. Obviously, when you use a simulator, you also have to specify all the power supplies. Okay. Now, from here onwards I will omit the power supply, but it is assumed that you have connected them up properly in the simulator. Okay. Now, let us say I have to simulate the loop gain. The reason to do that is I have to ascertain stability, phase margin, etc., and adjust my op amp parameters accordingly. Okay. So, what is loop gain? I break the loop here, I apply some V test and I find out V return. I plot the magnitude and phase of V return by V test, which is the negative of the loop gain, and from that I can ascertain the phase margin and stability characteristics. Okay. Now, this is fine, but how do we do this in practice? Because this needs a small signal incremental analysis. Like I said, you determine transfer functions using AC analysis, that is what we use for this particular case to determine the loop gain over frequency. But if we break the feedback loop, the DC operating point is also destroyed. We know that op amp circuits, or in general negative feedback circuits, need negative feedback not only for the operation, but also to set up the DC operating point. So, we must find a way that the operating point is not disturbed, but we are able to break the loop in some way and determine the small signal incremental gain or a small signal incremental transfer function in order to determine the loop gain. And when I compute loop gains, I set Vi to 0, that is what I will show here onwards. So, the circuit should look like this, the loop must be closed for DC analysis, but it must be open for AC analysis. Okay. And the loop gain is nothing but the negative of V return by V test, and this has to be done over a range of frequencies. You do AC analysis over a range of omega. Okay. So, how do we adjust this? Now, we have done things like this before, this is not difficult, right, because we have had cases where you have to AC couple signals, that means that the signal is applied for AC, but not for DC and so on. We will use a similar principle here, and what can be done is let us say we use a very large resistance, and because this is a simulator, this is not something that we implement in reality. This large resistance can be very large, okay, could be giga ohms also, although you cannot implement these things, you can put them in the simulator. We apply V test through a very large capacitor, this again can be unrealistically large, you can have farads or even kilofarads and so on. Okay. The bottom line is that R large should be so large that no current flows that way, and C large is so large that whatever voltage you apply here will appear there. Okay. And as usual, instead of a large resistance, you can also use a large inductance. Okay. Now, assuming that you have a MOS transistor circuit, the current here is usually 0. In that case, you can use a resistance. If the current here is not 0, let us say you use a bipolar transistor or some other MOS circuit where the current in this branch where you have broken the feedback loop is not 0, you use a large inductance instead, okay, because then there is no drop across the inductor at DC even if there is current flowing through it. Okay. So, you could use resistance or an inductance. The idea is to have the loop closed for DC. This makes sure that the loop is closed for DC, and C large which appears at some frequency beyond 0 will make sure that loop is broken for AC. Okay. Now, because you can use C large and R large which are unrealistically large values, this frequency limit can be very low, it can even be hertz or millihertz. Okay. But once you have this arrangement, you simply apply V test here, you plot V return as usual you apply V test of 1 angle 0, you get some V return, and you can plot the magnitude of V return. You expect it to be something like that, okay, versus omega, and you plot the phase of V return. Now, because V return by V test is the negative of the loop gain, this typically starts from a phase angle of minus 180 degrees, and it goes to 270, and then it goes off somewhere. Okay. Let us say this is minus 360 degrees. You can find where the magnitude becomes unity, okay, and the phase at that point, and the difference from this 360 degrees is the phase margin. The reason it starts from minus 180 is what we are plotting is V return, not minus V return. If you plot minus V return, it will start from 0, and you should find the difference between the phase angle at unity gain frequency and minus 180 degrees. Okay. So, that gives you the phase margin. So, from this you can ascertain whether the circuit has enough phase margin, and more importantly what you can do is you can plot the magnitude and phase at different stages. Okay. So, inside the op amp there may be 2 or 3 stages, you can plot the magnitude and phase, and you can also judge which stage is contributing predominantly to the magnitude roll off and the phase lag, and adjust the circuit parameters accordingly. Okay. So, this will help you design the feedback system so that it is stable. But finally, in any negative feedback system you have to make sure that once the loop is closed, the circuit behaves properly. Okay. That is, you do a transient analysis. Let us say you apply a step here, you could apply a small signal step and make sure that the output settles without significant ringing. Okay. So, basically to ascertain stability, what you do is you do AC analysis for loop gain with the loop broken, but the loop must be closed for DC, so that the operating point is established correctly, and you do a transient with closed loop and usually a step input, and make sure that the settling is clean. Okay. You have to do both of these, because the transient analysis is the real analysis, that is what happens in a real circuit. Okay. But sometimes it is difficult to gauge what parameter of the circuit to change if the transient response has a lot of ringing. Let us say you do the transient analysis, you get a lot of ringing, it may not be very easy to tell which part of the circuit to change to fix this. That is easier if you do the loop gain analysis and also find the gain magnitude and phase through different stages of the circuit, then you will know which part to change. Okay. Finally, there is one small detail that I omitted while discussing this. Whenever you break a loop, wherever it is, you have to be very careful about loading. I have assumed that I am breaking at the input of the MOS op amp. So, for DC of course, there is no loading, but looking into here there will be certain input capacitance. Okay. Now, when you break the loop, this node is no longer loaded by the input capacitance. Now, this is a very important thing in loop gain, because if you have this loaded by the capacitance, there will be some phase shift from this point to that point, otherwise there will not be anything. So, what you have to also do is to estimate the input capacitance and put it there. Okay. What can be done, for instance, is that let us say this is a conventional op amp with a differential pair M1 and M2 which are identical. What you can do to mimic the loading approximately is simply connect M2, okay, that is to this node you connect M2 and leave it there. Now, this is only approximate because what you see between the differential terminals is half the CGS of M1 and M2, and here we are getting the CGS of M2, but also this will not be in saturation region and so on. So, you can probably adjust the value of this one, but this will give you an estimate of the loading due to the input. Okay. This is again very important because if you simply break the loop and not take care of the loading, you could be missing out important phase shifts in the circuit. Okay. Now, one last thing, in modern simulators, because this loop gain analysis is used very often, you do not necessarily have to put a large resistor and capacitor to do this. I suggest that you do that anyway to get some practice and get a better understanding of the loop gain and concepts like that. But in modern circuit simulators, there are also facilities to, for instance, use a switch. Now, this switch again is not a real switch, it is a switch for analysis. You can specify that the switch is closed for DC operating point and open for AC. That is exactly what you want. For DC operating point, the loop must be closed so that the operating point is established, and for AC analysis it is open. Okay. And this, and there are also other more sophisticated ways of computing the loop gain. You can consult the simulator's manual for this, but the principle is exactly the same. In the loop has to be closed for DC operating point, but be open for AC analysis so that you can compute the loop gain. Okay. Now, one of the things with the simulators is that initially you have to have enough practice so that the simulator behaves as you expect. Okay. So, the only way to ensure this is by practicing with many simple circuits for which you already know the answer. Please do that. You can try it with both the linear circuits and simple nonlinear circuits, and then after that you can go on to more complicated circuits such as op amps, for which a simulator is indispensable. Thank you. I will see you in the next lecture.